Right. So I think we'll start if it's okay for everyone. So welcome to this PRAIRIE Colloquium. So it's a pleasure to welcome Raphaël Porcher for his talk today. Raphaël is a professor at Université de Paris of biostatistics. He is also the head of the Center Virchow-Villermé, Paris-Berlin. And I think he's also a practitioner, so a medical practitioner at APHP. And today, Raphaël will tell us about his latest work, I guess, in relation to individualized treatment strategy and machine learning. So, Raphaël, the floor is yours.
Thank you, Gabriel. Thanks, Gabriel and Jamal, for inviting me to this colloquium to give a talk. At the end of the talk, you will have some flavor of current work we are doing with François Grelot and François Petit, whom I would like to thank a lot. But mostly I will introduce the issues that I'm interested in for individualizing treatments. In my summary that you may have read or not, and I talked a bit about dynamic treatment regimes, but after doing the slides, I removed that for the sake of time. So you will have to invite me again to hear about dynamic treatment regimes. So we'll start with a brief introduction, and then we talk a bit more about the causal framework, how it fits with personalizing treatments, but also causal inference. We talk about observational studies and heterogeneity of treatment effects, and then we will get into the heart and individualized treatment rules and some issues that I think are interesting to look at. So the topic is about, from a medical point of view, the topic is about personalized medicine. So you might find personalized, stratified, precision medicine. All those terms are not exactly similar, but they refer to the same objective, which would be to deliver the right drug to the right patient at the right time. And the topic has mainly built on advances in patient genetics or molecular cellular analysis, like tumor molecular profiling and so on. The term was first coined in the context of genetics. So for many people, when we talk about precision medicine or personalized medicine, they think about one gene, one treatment, and that's done. But actually, the concept is much broader. And we try to adapt a broader view today. And I try not to find too many examples in cancer, for instance, even if it's the most active field in precision medicine. I think it's perhaps easier to look at it from a different angle. Now, the concept is by definition attractive. I mean, nobody could say, I'm not interested in personalized medicine. I would like the same drug for anyone at any time. I don't want to look at patients' characteristics. I don't want to do better. I want to do the same for all. So to that extent, yeah, personalized medicine is closely linked to medicine. Also, it has changed the views of cancer after some very promising results. It has generated so many hopes for patients, doctors, researchers, and also investments. But when we talk about more precisely, what are we looking for? We want to deliver the right drug to the right patients. And I will forget time now. This implies that we are able to associate treatment with the individual characteristics of the patient. So I will summarize those individual characteristics in a vector of that I call X. X is the patient's characteristics. And that's also why mostly the British have said that it's not personalized medicine, it's stratified medicine. Because all individuals who have the same X, and X may be huge, but may be not so huge. And if we think about cancer, often X is simply whether the tumor expresses some marker, or so X might be a scalar, indeed. And in that case, it's not so much personalized, it's stratified. We will give the treatment to a smaller slice of the population, the ones who have the same mutation, for which the tumor has the same mutation, but it's not so much personalized. So yeah, it's not the individual itself, but it's the individual reduced, which is a drastic reduction. I might accept that to a set of characteristics X. And that's the same reason why I will use rather individualized more than stratified wording. So we individualize the treatment looking at X, but it's not the person itself, it's just the X. And as an illustration, and I will take that example later on also, I will talk about coronary artery disease and not cancer yet. There were, for a long time, when you had a patient had a coronary artery disease, the solution was to do surgery and to do a coronary artery bypass grafting. In French, pontage coronarien, for those for whom it's easier to see that. And there was a big trial a few 10 years ago, about 10 years ago, a bit more, which is called the Syntax trial. And the Syntax trial has compared that treatment to percutaneous coronary intervention, la pose d'un stent in French. So you combine coronary angioplasty with a stent, which is a small device which will maintain the artery open. And that's for a population of patients who had previously untreated 3-vessel coronary disease or left main coronary artery disease, or both, which are 2 forms of the disease. At that time, CABG was the reference treatment, and actually it's still, after the trial it was still, and PCI was more and more performed without a clear evidence that it would be better. And the primary outcome, there were other outcomes, was a major adverse cardiac or cerebrovascular event, which is called MACE. And the results were that you had a higher rate of MACE with PCI, at 12 months. And the figures I've put here with MACE on the right and all-cause mortality on the left are not those of the main trial, but from the extended follow-up. So until 5 years here, and the primary outcome was 12 months, but then they have extended follow-up and a new paper with that. And this one shows the curves up to 5 years. And what we see is that the red curve, so the PCI curve, is above the blue one, and there is a higher rate of MACE. And MACE is deleterious. It's not a favorable outcome. It's unfavorable. We don't want MACE. We want to avoid MACE. So CABG does better than PCI in that trial. And if we look at how to interpret medical literature and at Gordon Guyat's recommendations, if a patient meets all the inclusion criteria of the trial, doesn't violate any of the exclusion criteria, there is little question that the results are applicable. So we should still keep recommending CABG and stop PCI for those patients. Well, but if it's the case, I'm done with my talk. Actually, the curves that we see are just averages. So the question is, okay, on average, CABG does better, but is the difference similar between everyone? Or are there some patients who would benefit from PCI? And that's called heterogeneous treatment effects. And if you have heterogeneous treatment effects, you might find individual treatment rooms, ITRs. To go even closer to that, I will first introduce you with Sarah and Donald, and thanks to François Grolot, I don't know if he is here, but he has found these examples that I like very much. So Sarah on the left is 59, she has diabetes, and Donald is 10 years older. He also has diabetes, but she receives insulin, he doesn't. She has a better ejection fraction than he does, higher creatinine clearance, and they don't have the same form of the disease here, left main coronary for Sarah, and 3-vessel artery disease for Donald. And the question is, are we sure that they shall both receive CABG? And then I'm done with them. We come back to them later on. Let's try to introduce you the framework where I would like you to study that. It's not my framework, of course. it's ubiquitous. Then you have also other paradigms possible, but the dominant one is the counterfactual model from Don Rubin. So we will consider a binary treatment that I will represent by a variable A for action. A is 0 when you get the control, could be here CABG, and 1 when you get the experimental treatment, could be PCI. And we are interested in an effect of A on the outcome. We already have a set of baseline covariates X. I call them baseline covariates because they are observed before we decide whether to give A or not, A1 or A0. And the outcome Y has a distribution that may depend on X. To define even the notion of a treatment effect on A on Y, we can do that in terms of so-called potential outcomes. So we will assume, but that's a view, because in fact you don't have those, but that's possibly a counterfactual, that's called a counterfactual model that could exist contrary to the facts. We assume there are two potential outcomes for any individual. One is the outcome, let's say, of Sarah if she receives PCI, and the other is also the outcome for Sarah if she receives CABG. So we call those outcomes Y of A being the treatment received, the treatment that we can set to A or not. If I were a surgeon or a cardiologist, which I'm not, I would be able to decide whether Sarah would undergo PCI or CABG. So we can set the treatment to A0 or A1. And then, of course, to be able to do any inference using observed data, we will assume an assumption that is called consistency, which means that if the treatment received was the small a, then we will observe the outcome observed Y will be Y of A. And if we do that, we can define the individual causal effect Y1 minus Y0. For Sarah, if I were able to know the outcome under CABG and PCI, I would be able to look at which one would be more favorable for her and to decide whether she would receive PCI or CABG. Of course, in practice, you cannot observe both, because if I have a surgeon doing PCI for her, she has a new bypass, a graft. She has that new artery. So I cannot re-operate her, remove the artery, put a stent, and look whether this has changed something. And even not talking about surgery, it's almost impossible to observe both in practice. That's the aim of crossover designs in some sense, or N-of-1 trials, but it's very, very specific designs that usually cannot be used. So what we do is more, sorry, so that was the individual causal effect that we will not have access to. What we usually do is to estimate the average treatment effect, which is simply the mean of that difference, the expectation over a defined population of Y1 minus Y0, and that we can estimate. But we could also estimate the conditional average treatment effect, CATE, which is the same thing, but conditional on a set of covariates X. And this one will be used for precision medicine. And then we can define a lot of other estimates or causal effects. And I will not dig into it now, but it's also an interesting thing. So what did syntax estimate? The randomization infers that the only difference between the two groups is the treatment. There is, by definition, the same distribution, true distribution of X between those who were in the A equal to 0 arm and those in the A equal arm, 1 arm. So the average potential outcome in one group is unbiased for the average outcome. Put it in math, the average of YA given the truth was the patient was in the A equal 1 arm is the same as if the patient had been in the other arm. And this estimates the expectation of YA, whatever A. So using consistency, I can relate the observed Y to Y1 in group 1 and to Y0 in group 0. But since I have consistency plus randomization, the difference of the group means estimates the average treatment effect. So RCTs give us an estimate of the average treatment effect. Can we make it individualized? Of course. Let's consider the same but condition X for the same reasons as before. The randomized trial allows us to estimate the causal average treatment effect. And I will term it, so the expectancy of Y1 minus Y0 given X equals small x, I will term it tau of X. Those who with a tau of X positive, or if we are or negative, I don't, well, let's assume that high values are favorable. So those with tau of X positive benefit from A equals 1, and those with tau of X negative benefit from A equals 0. Actually, for the syntax, it's the contrary. The high values of Y are not beneficial, are negative, maleficial. So we should take the reverse, but that's the same. So those who have tau of X equals 0 are in a real equipoise. Each treatment does the same, and on one side you have those who benefit from one treatment and the others who benefit from the other treatment. And if we we follow the natural strategy, which is to give the treatment from which the patients benefit more, we get an optimal treatment strategy. But in practice, for that, you need to know tau. And most of the work about individualized treatments would be either to get an idea of what tau of X is, or directly to find a rule which optimizes the treatment strategy. And we'll come to that later. More generally, we can define any individualized treatment rule as R of X, taking values in 0, 1, which indicates which treatment, which value of A, one will recommend when X is equal to the small x. So if R is simply the treatment that will be recommended by a rule. And I will note Y star of R, the potential outcome under a rule R, which is Y1 R of X plus Y0 1 minus R of X. So if R says you take treatment 1, we will have Y1, and if R says you take treatment 0, we have Y0. Okay, we've seen that in the randomized trial setting, we can estimate the average treatment effect or the conditional average treatment effect. So we have everything we want. But I will still talk about observational studies because I need it later on, and also because one issue with randomized trials is sample size. The syntax trial is a big one, but most trials are much smaller, and they are just powered enough to detect an average treatment effect, and often they are clearly underpowered to allow reliable estimation of conditional average treatment effect. But we can use observational studies. Observational studies are studies where there is no control on the people who do the study on the treatment assignment. We call that often also real-world evidence, real-world studies. You just observe what has been done and you collect data. And by doing so, and even more today that we have electronic health records, we have access to big databases, we will have much larger amounts of information than in trials, or at least much larger amounts of individuals. The problem is that the level of treatment A might be related to the prognosis of outcome, to the prediction of the outcome under reference treatment, which is called confounding, and which is the most studied concept for epidemiologists. They are crazy about confounding, and so the Y of A depends on X and the treatment A as well. Therefore, the couple Y0, Y1 is no more independent of A, and we are able to estimate the mean of YA given capital A was A and X, but we are not able to estimate easily the expectancy of YA anymore, because A depends on X, Y depends on A, YA depends on X also. So we cannot cut that conditioning here, at least not easily. Of course we can, otherwise there will be no presentation. Under some assumptions, actually, it is possible to estimate the aforementioned causal effects with observational data. And there are different sets of assumptions depending on what you like to estimate and how you want to estimate it. But most frequent are consistency, but consistency, we have seen that before. No interference, no unmeasured confounders, but you might do that with other assumptions that are, for instance, instrumental variables, positivity, and sometimes a model relating the potential outcomes to treatments and covariates. And by using all or a part of those assumptions, we can do something. And one very central assumption is what we call also Theta, strongly ignorable treatment assignments. So this is a combination of two previously mentioned assumptions: no unmeasured confounding and positivity. No unmeasured confounding means that in my baseline covariate X, I have everything that is linked to both A and Y, so that the Y1, Y0 will be independent of A given X. The potential outcome do not depend on the actual treatment given X. And this is very, very useful to allow causal inference. Because if I can do that, if we can assume that by consistency, we can relate the observed Y to YA in group A, and by the conditioning on X, we will get an estimate of the mean of YA given X. And the other useful assumption to be able to use that is positivity, which means that basically all patients in the study will have a probability of receiving A given their covariates, which is strictly above 0 and strictly under 1. It's never 0 or 1. To put it blankly, if you have individuals who, given their covariates, always receive the same treatment or never receive the treatment, there will be no information to compare with the other treatment for them. So you cannot make any inference about the treatment effect for them, or you have to add additional assumptions. So once we have those assumptions, we can identify the causal effect. This is not so complicated. We are looking for the expectancy of YA, and we can write it as the expectancy over X of the conditional mean, the conditional expectancy of YA given X, because of positivity, because of a theta. Then, sorry, I take it the wrong way. So this one is easy. It's just a definition of the conditional the expectancy. So the step before is that you will get you can relate that quantity, this one, to this one by no measure confounding and positivity, and to the observed by consistency. So by adding those assumptions, we are able to make causal inference and to estimate the enrichment effect by conditioning on X. So in practice, we use model assumptions for some parts of the joint distribution of all the observed variables, either for the distribution of A given X, which is using the propensity score, or for the distribution of the outcome Y given A and X, which is using an outcome model, and sometimes we use both. If I'm not too long, I'll briefly go to the key properties of the propensity score. So the propensity score is something very, very simple. It's just the probability of receiving the treatment A given the covariates X. And it has two key properties. One is that it is a coarsest balanced score, which means that the covariates X are independent of A given the propensity score. So the finest balanced score is X itself. But if you summarize X by E of X, propensity score, you get the same balancing property. And under theta, the propensity score is sufficient to control for confounding. So what I have written before by conditioning of an X, you can do it by conditioning on the propensity score. And it also works with the estimated propensity score in data. And that has been central for using causal inference in practice. In practice, when people do propensity score-based analysis, they can use the propensity score as a covariate in regression. They stratify by categories of the propensity score. They match or they weight. And I will go to weighting because we use it later on. Weighting is a view that to look at weighting, we can consider that when A equal 1, for instance, we have observed Y1, but we have when A equals 0, Y1 is missing. So we want to predict missingness, and to predict missingness using covariates, we have the propensity score, which is the probability of Y1 being missing. And then we use it. We use that very simple trick here to reweight the sample, and then we can estimate the mean of Y1 simply as the weighted mean in the data of the observed Y's, but weighted by 1 over the estimated propensity score. And similarly, in the other group, we can estimate the mean of Y0 by using 1 minus propensity score weights, 1 over 1 minus the propensity score weight. And when we do that, we produce a pseudo sample, a reweighted sample, where we have made A and X independent. So the weighted sample mean is an unbiased estimate of the mean. To go further, if we use that estimator, the IPW estimator here, we have to plug the estimated propensity score. It has been shown that it's even more, if the model for the propensity score is correct, then that estimator is even more efficient than the one using the true propensity score, because it's also correct for random imbalance. But if the model is misspecified, the propensity score model is misspecified, then IPW can be biased. And to overcome that difficulty, there have been IPW, augmented IPW estimators proposed, which looks very much as this one, but there is an added term here on the right, which uses a model for the outcome given the covariates. And then I see that I have changed the order of my slides, and then you have no definition of new one. It's simply a regression model for the outcome in the group A equals 1 given X. it was defined, but then the slides has been moved later on, and I forgot that I had this one. I'm sorry. So AI-PW is consistent if either the propensity score model or the outcome regression model is correctly specified. This is a nice property in theory, but in practice it's not so useful. But it's called double robustness. But generally, it's more efficient than IPW, and that's a more interesting property in practice. So now that I have introduced all that, and I'm sorry if it was long, if you already know that. By the way, if you want to interrupt me and ask questions, I'm happy to answer questions whenever you want. We can go back to the heterogeneity of treatment effect, because that was the topic of the talk. Let's go back to personalization. I've used X for actually different sets of variables. I have used X to talk about confounders, but also prognostic factors at some point. And for instance, this one here, it is a prognostic model. So it's a model for the outcome given X. So those are a part of the prognostic factors, but not all prognostic factors are confounders, because there might be prognostic factors that are not associated with the treatment given A in an observational data. Conversely, in a randomized trial, you don't have confounders because you have randomization, but you still have prognostic factors. And then I have also used X when I talk about tau of X, the conditional average treatment effect. Those are effect modifiers. Those are not necessarily confounders, but they might be. They are prognostic in some sense, for sure, but they modify the treatment effect. So X can be used for all those different meanings, and sometimes it's not the same set of X which is interested in which we are interested in, but we still have to always keep in mind what X we are using. And talking about effect modifiers, there is something which is not straightforward. I'm sure it will be straightforward for you once I have told you, but perhaps you never thought about this before. So this deserves a small presentation. Up to now, I've always spoken about the average. I didn't talk about Y, but it looks like Y was in my mind something a continuous variable, and an effect modifier was X was such as if I take two different values of X, my conditional average treatment effect is not the same. So X here modifies the conditional average treatment effect. So it's an effect modifier. And this is a natural scale for a continuous Y. But in clinical research, and I'm sorry, there are two buts, most outcomes are binary or censored. And let's take a binary outcome. We could do something with survival too, but it's simpler with binary. To summarize the treatment effect for a binary outcome, actually we have different metrics. One is I'm sorry with the parentheses, I messed up something here. But the risk difference is simply the difference of the probability that y1 equals 0 equal 1 and y0 equal 1. So that's the average difference in the same sense as before. It's on the absolute risk scale. If we have a risk difference of 20%, this means that on average, the risk of event is 20% higher, or risk may mean something wrong. Let's say a risk difference, a risk reduction of 20% means that the risk of dying, for instance, is 20% lower with the treatment than without, on average. But we could also measure it as a relative risk or a risk ratio, which is the ratio of the two probabilities or the two expectancies, same for a binary variable. So we may say, for on average, the treatment reduces the risk by 20%, a relative 20%. So the relative risk is 0.8. The risk with the treatment is 80% of the risk without treatment. And you might also have the odds ratio as a relevant scale to measure the treatment effect. But what occurs here is that the treatment effect can hardly, if it's not null, it will not be constant over all the three scales. Let's assume that there is X, which is a prognostic factor. So the probability of Y0 equal 1 given X varies between 10% and 80% along the range of X. And this has that shape. Now assume that the treatment will reduce the risk by an absolute 5%. So those who have 10% risk go down to 5%, and those who were at 80% go down to 75%. In that case, you have a blue line here, it's minus 5%. For everyone, whatever X, the treatment reduces the risk by 5%. In that case, if you look at the relative risk in yellow, no, sorry. Now we look at the relative risk here in blue. For those who had 10% risk who are down to 5%, the risk is divided by 2. You have a risk ratio of 0.5. But for those who had a higher risk, the risk ratio is much lower. And actually, it's more than 0.9. So you have a heterogeneity of the treatment effect on the risk ratio scale. And that's the same for the odds ratio. Conversely, we can take a constant relative risk or risk ratio of 0.75 here in yellow, and then you will have a non-constant risk difference and a non-constant odds ratio, and the same for the odds ratio. So actually, for a binary outcome, as soon as you have prognostic factors, so variables that make the baseline risk not the same, you always will have, to some extent, treatment effect modifiers, because you can't have the same treatment effect on all the scales. Okay, now we can go to individualized treatment rules, and I'm sorry for that so long an introduction, but I think I needed all the bricks to explain the issues with individualized treatment rules. So what we would like is to estimate this CATE tau of X, and then find a rule, a treatment rule, which would be, for instance, 1 if hat tau of X is positive or negative, depending on whether Y is beneficial or not. Or we could try directly to find an optimal rule, allocation rule R. And we can do that using either data from a randomized controlled trial, but we have already said before that the main limit is the sample size. We can use a series of randomized trials, and which is called an individual patient data meta-analysis. And if we do that, we gather more data, and we'll have to account for clustering, but we can do something. Or observation data, but in that case, we have to be very careful on the confounders. And once I've said that, you can look how many methods exist to either estimate the CATE or a rule R, and you find hundreds of them. And they range from the simplest approach to much more refined ones. And I will just give you some ideas of what people have done there. For instance, I like the TSX learner wording, so I use them more than what it was done or in a more general sense than they were used previously at the beginning. But I think it's interesting like that. So the most basic idea would be, well, if I can fit a function mu of a of x, which is which is the mean of ya given x, using data from each group, a equal 1 and a equal 0, then once I have estimates for mu1 and mu0, I can form the treatment, the individualized treatment effect, the CAT, and that's straightforward. So you can do that using a regression model or any supervised learner, and you do that. And it's called a T learner because you fit 2 learners, 2 models, T for 2. That's the easiest way to do it. You just learned mu1, mu0, and you form the differences, and you get an estimate of the treatment effect for a given x. Another option would be to fit only one response function using the treatment as a covariate. Say, well, the treatment A was one covariate like the others, so I only have one model to fit, which depends on x and A, and I use all the data together. When you use a regression model, a simple regression model like a linear regression, then you put interactions between A and X here, but you can use any other learner you want. And then you will form the hat T will be simply the difference between the hat mu X A equal 1 and hat mu X equal 0. And then you have many other refinements on those, like the X learner, R learner, and so on. Another class of methods aims at estimating the optimal treatment regime directly. And I will have a focus here just on one method, which is a double robust estimator. It's quite general, so I think it's easier to see. So we first consider a big class J that are indexed by eta of rules, and R eta of x is a function of x and eta, and R is a rule. And we find an estimator for the mean of y star under rule R eta, and we try to maximize it in eta, which gives us hat eta, and we just get the optimal rule, which is the R x and hat eta hat, sorry, that we have found. So to do that, we first define a new variable, which is C, also indexed by eta, which is what I have called before. What was my notation for it? I don't remember. Which is A equal to, no, perhaps I didn't use it before. Sorry. It's A times the rule plus 1 minus A times 1 minus the rule, which means which treatment patients received according to the rule. And then I have a sort of a new propensity score, which is the probability that to have followed the rule. So C eta indicates whether the rule and the treatment match, A1 R1 or A0 R0. So whether the treatment received by someone matched the treatment indicated by the rule. And we can form an IPW estimator of eta using the same IPW estimator we had before, except that instead of A, we put C of eta, and instead of the propensity score for the treatment, we put here the propensity score for the compliance to the rule. And similarly, as I have done before, we can also imagine the double robust estimator of the same. with the same here correction. So it's IPW estimator, and here M is a regression model for the mean of Y star under the rule R eta given X. Not the same as before. But if you do that, you try to maximize this in eta, and so you will find the rule that maximizes the average of Y in the population if you follow the rule. And you have other options like outcome weighted learning, A-learning, and so on. And I think I have no time to go into this. Then you still have other approaches like the virtual twins. Virtual twins. Those are less general, but more complex. You first start by T or S learner. You get individualized treatment effects, though the tau hat in the observed X, and then you build either a classification tree by dichotomizing DI at a predefined value delta, or a regression tree and then dichotomizing. And by that tree, you get a subset of individuals who are benefiting from the treatment more than delta, and then you estimate the benefit of the treatment effect in A. Or other algorithms, and then we go back to the example. I have no time. So there is a wealth of methods. One simple application is the syntax score tool here. It's it was developed some years ago, updated end of last year. Basically, they have done an S learner, so they have used the Cox regression for the syntax data, which is about 1,800 patients. They have used Cox regression with the interactions and to predict 4-year mortality according to baseline characteristics. And then they have redeveloped it to predict 10-year mortality. And you see here a double nomogram. So you can compute the risk of a MACE or mortality here, sorry, if someone received CABG according to the individual characteristics, the same for PCI, and you compute both and you make the difference, and this is an estimate of the individualized treatment effect. Further, they have in that paper, for instance, that they can show us how it is distributed in the population. So the scale is not the absolute value here, but the log hazard scale, but otherwise it's similar. So you have here the people for whom the hazard will be lower with CABG than with PCI, and on the contrary, here you have the people for whom the hazard is lower with PCI than CABG. And the gray points are the ones who are in confident within an uncertainty interval. So those for whom the confidence interval of the prediction does contain 0. So for whom we cannot be sure that one treatment is better than the other, at least at some level. So this is for the left main disease, and this is for the 3-vessel disease. For instance, you see here for 3-vessel disease, it's very, very rare that PCI would be better, but for left main, it's more balanced. So we can go back to Sarah and Donald. And you can use a calculator, and actually there is an online calculator that has been used to do that. So for Sarah, if you do that with the updated data, so 10-year mortality and 5-year MACE, what I've shown before, it was 4-year mortality. You can do it for 10-year mortality and 5-year MACE. You compute that with PCA and CABG, and you see that the risk is slightly lower with PCI than with CABG. So it seems that for her, PCI might be a better choice, though there is no big difference between both. And for Donald, on the contrary, he has a 3-vessel artery disease. I don't know if you remember, but for those, CABG does often do better. And for him, there is no doubt that CABG will be recommended because the risk is much, much lower than with PCI, both for mortality and MICs. So this is how it could be used. Now, some issues. The methods introduced before used mostly RCTs, but some observational data to estimate a rule or events. If you have used machine learning with tuning parameters, in general, you will not get a consistent estimator of the CATE. Moreover, the ultimate validation step of the individual treatment rule would be to conduct a randomized trial that will compare the implementation of R to usual care. Perhaps that Sarah, if she was managed by a physician in usual care, she would receive a PCI. And there is no need, perhaps, for those exact calculations for her to receive PCI. And Donald would likely receive CABG. So perhaps the rule does so much differently as the doctors usually do. Or perhaps the rule does much better, but this deserves investigation. Such a randomized trial is difficult to conduct in practice, and there are very few of them in cancer with simple rules, but for other domains I never saw that. But one could also use observational data to estimate the effect of implementing R. No more estimating R. We take an R and we want to estimate the effect of R in the population. It's almost straightforward when we compare A equal 1 to A equal 0, because we have methods that I've talked about before, score, double robust estimators, and many others that I didn't talk about. Comparing R to usual care is a bit more complex because the same individual could comply with R, but also comply with usual care, because for some people, many people, most of the people, I don't know, R and the usual care might match. So we have to take that into account, and then we could remark that actually the benefit of implementing a rule only relies on those who would not receive the treatment recommended by R under usual care. So there is only a subset of the patients for whom we change the treatment, and then the benefit depends on them. So we can define an average rule effect, or at least we have termed it that way, perhaps. So we define Y star R as before, and Y star U under usual care, which is the expected, the outcome that one would have under either following the rule or just under usual care. And the effect of the rule, theta, is simply the mean of the difference between both. And using a propensity score, one can write theta in two different ways. First, one can do easy calculation and show that it's the mean of tau of x weighted by the difference between the rule and the propensity score. The benefit of a rule will depend both on the individualized treatment effect. If it's almost constant for everyone, it will have less effect than if it has big benefits in some places. And also how much the rule differs from the usual care. The propensity score in observational data is the usual care, how people have given the treatment, given X. And when R and E are close, I know R is binary and E is a probability, but still when they are close, it means that the rule matches pretty well with usual care. But in that case, there is no big improvement to expect, because we will not do much better than usual care, except if we do that for extremely high tau values. On the contrary, when the rule is quite different from usual care, then we can expect a better benefit. And we can rewrite theta differently too. And this suggests an IPW estimator of theta, for instance, and we can derive a double robust IPW version of it. And that's rather straightforward. Which is less straightforward to estimate the variance of that, and François is working on that. The other issue is that individualization. For now, I have always spoken about why, but the truth is that the effect of a treatment is not a single why. Often it's multidimensional. Let's look at that example of intensive antihypertensive treatment. We can use prediction models for benefit. There have been, prediction models for benefits and harms, but there are two dimensions: the benefit, so the avoiding cardiovascular events and death over 5 years, but you have also harms in having an intensive antihypertensive treatment. And there is a balance to do between both. And what we showed here, for instance, was that if you used prediction models for deriving ITRs for the benefit, which account for both the benefit and the harm, we could reduce a bit the benefit, because we will avoid slightly less cardiovascular events, but we will avoid much more serious adverse event, and perhaps there is a balance to find. So when developing ITRs, I'm convinced that we should look at optimizing not a single outcome, but the balance, at least between one measure of benefit and one measure of harms. And I recognize that it's more complex, and you might have many different measures of benefit and harms, but already taking into account one benefit and one measure of benefit, one measure of harm would be nice. Another question would be what could occur if not everyone follows the ITR? ITR is a rule, but we know doctors don't follow the guidelines. A rule is like a guideline, and we know that physicians deviate from guidelines for many reasons. And I'm sorry, I mean, so many typos here. They deviate from guidelines because of lack of knowledge, but also because they adapt to specific cases. That's a true personalization. The rule says you should do that, but the patient says, I am afraid of surgery. So you go to PCI because the patient doesn't want CABG, even if the model would recommend CABG. That's personalization, actually. But so much personalization that it's not, I'm not able to formalize it by X. And the patient opinion has to be taken into account. So there is also the trust of the recommendation. For instance, here you had a lot of gray points. So there are a lot of points where I'm not so sure that one is better than the other. Here, there is likely uncertainty. So I'm not so sure that CABG is worse than PCI for her. Here, I'm pretty sure it is better. So the one thing we can look at is the impact of adhering to the rule on the absolute average rule effect. So François, another François colleague of mine, is working on that. We imagine different scenarios for implementing an ITR. We either accounting for uncertainty, so for instance, the gray points, and then the level of confidence that you put shows how much you are ready to accept or not. But the gray points would not lead to change treatments, but the black would. We can model resistance to change, like cognitive bias, which would make the difference between the probability of following the rule depending on the difference between what the rule says and what the propensity score says, which is what physicians usually do. And the more the rule is different from the usual setting, the less chance you have to follow the rule, because in practice, physicians will be reluctant to completely change the management of someone. And then you could add more complex situations or random adoption of rules. Also, you can do that. And so this is an example on a simulated data set which mimics syntax 2, just to show you that needing some level of confidence can result in poor adoption and poor benefit, but you can have almost the full benefit of the rule if it was perfect and perfectly implemented, even if you deviate a bit from the total adoption. And in the other case where you have cognitive bias, you never reach the diagonal, and that's because of this formula here. So if the benefit is where R is not equals, is far from E, but if we model the adoption of the rule as low probability of adopting the rule when R is far from E, basically people will follow the rule where there is no specific benefit of following the rule compared to not. So this is a work in progress, but this is what we are thinking about. And also, I think that we should account for that sort of bias when developing the rule itself. Perhaps it's no more optimal according to the traditional criteria, but to be useful in practice, I think that the rule should be implemented and implementable by physicians. So what we recommend is contrary to common knowledge, we might be right, but it will be difficult to get people changed. So perhaps it's more valuable to have less optimality, but more adoption. And that's something that I think should be taken into account. Okay, I don't have really a conclusion to that talk. I would like to thank you for listening. I'm ready to take questions. Just to summarize, the precision medicine, individual treatment rules is a very, very active field of research, and there are a lot of machine learning techniques developed. There is still a lot to do. It's more a matter of use. In practice, people don't use it so much for medical decision making. And so I think we should do a lot on that and how to make something usable. How can we go really up to that? And I think this also raises interesting questions. Thank you. I'm ready to take any question.
Thank you, Raphaël, for your talk. So yes, we can have questions. So people can basically unmute their mic or post on the chat. So maybe just can you say a bit more? But you say that this is not really used in practice. I mean, what do you mean by this? And is it like really not used? And what would be the?
Sorry?
You said it's barely used in practice, individual treatments, but does it mean that it's never used, or I mean?
Okay.
And you in your practical, maybe about you, I mean.
In cancer, it's used, but it's not used. Well, the models behind are not so much interesting from a machine learning or a mathematical point of view. That often you only have the algorithm only makes a correspondence between molecular alteration and drugs targeting that alteration. So this is used in everyday practice everywhere in cancer, but it's just like you have done smaller slices of the disease, and you say, no, it's not a malignant melanoma, but it's a BRAF mutated malignant melanoma. But using models such as the syntax score to decide between PCI or CABG in everyday practice is not yet really implemented. I think it will be, but to do that, you need a decision support system. We cannot expect a physician. Well, now you have the web app here, but otherwise you cannot expect a physician printing that, looking at the variables, drawing a line, counting the points, and then looking at the curves. That's not very practical. So with an app, you can have that. But then you see here, it's it's not even 3% difference. And are we sure we are not in the gray zone? And once you go for a decision, then the physician is liable for the decision, for instance. So it might be used as an help. You can present that to Sarah and say, look, PCI is percutaneous, you just get a stent. Yes, on average, the people you've talked before says it's less good than PCABG, but for you, it looks better. It can be used as a personalization tool, but it's difficult to use it in practice yet, but I think it's going to be at some point, and people are developing some systems, but it's not yet the common way people are treated.
Okay.
Well, maybe I have a question, Gabriel.
Yeah, of course. Go ahead. Go ahead.
Okay. Thank you, Raphaël, for this very great talk. I learned so much about the topic. We start working on that with Florian, which who is in the audience too. So this it answers a lot of questions we had. Here in the conclusion, you mentioned that there are a lot of machine learning techniques that are being developed.
Yeah.
What kind of methods you're aware?
Yeah. Okay. Yeah, you have people have done causal random forest, for instance. X-learner is machine learning. Actually, you can put any machine learning in T-learner or S-learner. So people doing that are people from machine learning, like for me, machine learning, but perhaps for you not, but like Stefan Wager or people like that. So either you plug in, for instance, if you use random forest in I would call machine learning very specific, though it when then you have a causal random forest, for instance. Causal random forest. Some people have done neural networks for that, but I don't know very well the paper. It is a field where outcome-weighted learning, people are looking at that from many different views, A-learning. So you have a lot of everything that could apply for dynamic treatment regimes with Q-learning might apply to a static regime, as I talked here also.
Yeah. And what is your opinion about these works? Do you believe in these works or not?
You are asking me a very difficult question. What I no, but okay, there are margins of improvement at any possible level. So if you take, can I go back to the slides? So Zhang and Ciatis have done that, and it's well, now it depends. It will depend very much on how you are able to estimate p hat and m hat. So if you are efficient in those, perhaps it's better. So there are many ways to improve on that. Others have noted that, for instance, when you just fit those regression models, you spend a lot, you lose a lot, or you lose in trying to learn what you're not interested in, which is, for instance, mu zero. Mu naught of X is not interesting by itself because it's not the treatment effect. It's just the average, the outcome, the conditional outcome in the non-treatment group. So there are people who have proposed methods just focusing on the tau of X. So you don't estimate everything, you just target this tau of X as an estimate. But since the rule is not smooth, then there are ways to the optimization is not easy, because to optimize generally you need to have something smooth, and the rule is binary, so it's not smooth. So there are different ways to try. So I think there are a lot of things to do to improve on that, but it's small improvements.
So there is a question of Florian also in the chat.
Okay, so compliance. I don't. Okay, I talk about compliance to the rule. Florian, is Florian talking about compliance to treatment? So like the causal average, compliance average causal effect, or yeah, okay, compliance to treatment. So for now, I have talked about the compliance to the rule at the end. So whether the rule is adopted by physicians, but you might also add compliance. Actually, there are works on compliance average causal effect, so which aims at estimating the treatment effect among those who comply to the rule, to the treatment. Sorry, you could develop the same for a rule. I assume that. So either you could say, well, I want a rule, a treatment rule, which accounts for the probability of complying to the treatment, which I'm sure you could incorporate that. So if you do that, you will try to tailor the rule to the ones who are most likely to benefit from the treatment you will recommend, but also benefit from it, and benefit also because they take it. So is that what you mean, Florian? I think this is definitely something that we can do. Which is in the treatment effect, there is the average treatment effect, even conditional is average, but also there are people that you could predict will not take the drug or will not comply. So not in the CABG example, because that's a one shot, but if it's a drug, people won't take it. If you don't take it, you can't benefit to it. So if you incorporate that in your rule, I think you will also have a better outcome on average, because you will have targeted the ones who benefit. So that's really interesting, Florian. I think it's an excellent suggestion to have patients compliance. For now, we had just taken about physicians compliance to the rule itself, but the rule could account for the fact that the patients would or would not take the drug. So it's not the best drug, but it's the best drug for those who will take it. Excellent solution.
Great. Great suggestion, great answer. So I think it's time to stop the colloquium. Thanks, Raphaël, for your talk. Always feel a bit weird not to say thank you in presence, but it was a great talk. See you everyone. Yeah. See you everyone. So next month, sorry, for Max Welling colloquium on deep learning, it would be on the 16th of June.